Hi, today we are going to use the efficient pre-trained model in order to classify sports images. For example, we are going to classify this image, and we are expecting that our model, after training thousands of images, try to predict that it is a water polo image. So first of all, we will download our dataset. As you can see, this is the Kaggle link, the Kaggle website. There are several categories like athletics, football, rugby, water polo, and in each category we have thousands of images. So basically we will download this dataset to our local machine and build a model based on the efficient pre-trained model. So basically this is the target of our today's tutorial. So let's start. Let's create a new Python file. Of course, I will leave a link in my video description for the code. So the first Python code will be as preparing the data. That means splitting the dataset into trained dataset and test dataset, and I will explain how to do it using Python coding. So first of all, we will import the necessary libraries. We began with importing the required OS, shutil, and random. The random library will help us to randomize the images between the train and the test folder. So this will help us to perform all the file operations and all the randomization in this process. So let's establish that 90% of the dataset will go into the training folder, while the remaining 10% will go into the test folder. Now we will set the main dataset folder. We will specify it using the variable main folder, and then we will create a train and test directories using the os make dirs function. Of course, we are checking if the directories are not exists. If not, we are creating these new directories for the train and the test. Let's copy that, the same for the test. It should be make deals. Okay, now it's correct. Okay, next we will retrieve the list of the subfolders. We will initiate an empty list called subfolders to store the subfolders within the main dataset folder. We check if the item obtained from the main folder iteration is indeed a subfolder, and if it's a subfolder, we add its path to the subfolder list. Now we set a percentage of the data that will be allocated to the training set as 90%, and we iterate through each folder found in the main dataset folder. We extract the name of the subfolder using the base name function, and then we will create the train and the test subfolder using the path join and the make deals function. Let's do the same for the test folder, the test subfolder, of course. And now we are creating those subfolders, the train and the test. Now we will list all the files in the subfolders. We use the scan dir to obtain the list of all the files within the current folder. So now we got the list of all the images. Next, we will shuffle the files. We shuffle the list of the files randomly, so ensure the randomness in the distribution of the data between train and test dataset. Next, we will calculate the number of the train files. We will calculate the number of files that will be allocated to the training set based on the specific percentage, which is 90%. And next, we will copy those chosen images to the train folder. We will use a loop in order to copy the calculated number of files into the train subfolder. Okay, this is the copy process using the SHUtil. We are copying all the chosen train images. This will be the first loop, and the second loop is copying all the test images. So the test images, basically it's the same Python command, but the real change is this one. It's all the rest images that were not chosen for the train. And of course we have to change the target folder, which is test folder. So let's add a final message that the process has ended, and let's run it. Let's jump directly to our target folder. So this is the train target folder. As you can see, already 3 subfolders has been created. If we will wait every few seconds, a new subfolder is being created with all the images inside these subfolders. Each subfolder is representing a category in our model. So as you can see, each time a new folder is being created, and now it's done. Let's jump into each of these subfolders. Let's go to the test folders. As you can see, we have images in each of the test folders. So now let's start to build our model. We will use, as I said, the efficient model, and we will do a transfer learning using this EfficientNet version 2 model. Okay, let's continue coding, and we will start building our model, or basically adjusting and do fine-tune and transfer learning for the EfficientNet version 2 model. We will start with import the necessary modules. We will use TensorFlow. So let's include layers and image data generator, which will help us to build and pre-process our data. And we need more Python libraries such as NumPy. It's very relevant for doing some transfer to our, or maybe transformation for our images. And we will also use a matplotlib to display the results of our model. Our image size will be 224. We basically will resize all our images to this dimension. Okay. Now the next process will be getting the class's name. the class's name, we can retrieve this information out of our dataset, this Olympics image dataset. So we will specify the path to the main dataset folder and then retrieve the class names, which basically are the subfolder names. And basically what we need in this step is the number of classes. It's a crucial argument for our model. Let's run it. Okay, let's wait for the results. Right, we have 10 classes. These are the names and this is the number. We will also use the same function at the last step, at the final step of the prediction, to get the class name, but as for now we only need the number of classes. Next we will load our model. We will load this pre-trained model using TensorFlow Keras applications. This load process helps us to load all the weights, the existing weights of this model. But as you can see, it was pre-trained with the ImageNet. That means that the last layer expects to predict 1000 images. But we need only 10 and we have our own dataset. So we will chop the last layer using the include top false argument, and then we will replace it with our own layers. Now we will set the base model with the trainable parameter to true. This allows us to fine-tune its layers during the training. So we will use the existing weights, but we will train it to our own needs. Okay, let's continue to the next step. Now we will create a new model by stacking additional layers on the top of the pre-trained base model. This will include several layers. As you can see, we are adding a global average pooling, and then we will add 2 dense layers with a ReLU activation function. Then we will add a dropout of 50%. That means that during the training 50% of the filters of the neurons will be drop off. This will help us to avoid overfitting. And the final dense layer, which of course will be a softmax activation function, this will be filled with our unique number of classes. We have 10 classes, and then we are ready to go to the next step, which is compiling our model. Now let's define our optimizer. We will use the Adam optimizer. And since we are doing a fine-tuning process, we will define a very low railing rate. As mentioned earlier, I will also leave a link in the description for this code as well. Next, we will compile our model. We will use a categorical cross entropy as the loss function, and we will define the accuracy as our matrix during the training. Okay, now we are loading and pre-processing our data. In order to do that, we will use the image data generator function to load and pre-process our training data and the testing data. We will also use data augmentation techniques like rescaling, resharing, and zooming the images. The main purpose is to enlarge our dataset. So we will use some horizontal flipping, and we will apply all these data augmentation arguments to our dataset during the loading of the dataset. As for the test dataset, we only doing the normalization of the data. That means that since each pixel is between 0 and 255, we will normalize it between 0 and 1 by dividing the values by 255. Now we're using the flow from directory function in order to load the data. We define the data generators for the training and for the testing, specifying the parameters, like what is the name of the source folder for the train images, what should be the image size. As I said earlier, we are resizing all the images to 224 by 224. We will define a batch size of 8. That means that each 8 images will be collected together as a one batch. The class mode is categorical, since we have more than one class, and of course we are loading in color images, not the grayscale images. And let's also shuffle the images during the load process. Let's copy this command for the test generator as well. Basically it will be very similar to the train. We will replace the name of the test generator and replace the name of the images folder, and we don't need to shuffle all the test images, so this will do the job. Let's run it. Okay, let's wait for the loading results. As you can see, we have 9 images for the train and 1 images for the test. And let's define the training parameter, like the number of epochs, which will be 300. And also let's define the name of the saved model. Each time the model will be improved during the training, let's save a new and fresh weights file. And this will be the place that this file will be created and stored. Now let's define the callbacks. And the callbacks, we will define the checkpoints and the reduction of the learning rate using on plateau and the early stopping based on the validation accuracy. Basically, we are going to not wait all the 300 epochs, but we will do adjustments during the training. For example, if the training is not performing well during several epochs, we can change and reduce the value of the learning rate, and this helps the model do some changes during the training. Also, we will use the early stopping function in order to investigate the validation accuracy. That means that if the model is not improved during the training, then we will stop the training because it's become non-relevant. And if the validation accuracy is being improved during the training from the last epoch, it will be stored in our best model file, and if not, it will count 25 epochs, and after 25 epochs the model will stop training. Now it's the training process. Using the Feit function, we will send all the relevant arguments. The train generator that has all the images for the train process that we defined earlier with all the data augmentation divided by batches and everything inside it. The epochs, which will be 300 epochs, the validation data, and the callbacks that we defined earlier. And after the training, we would like to get the highest validation accuracy. So let's get using the argmax function. We will extract it from the result variable. It's a return variable from the training process. And let's print it. You can understand that all the training process, all the history of each of the epochs is stored in the result variable. And now we are extracting the validation accuracy and retrieving the best value. So let's extract it and print it after the training. But in order to understand if the model has finished with a good result, that we don't have any overfitting or underfitting, it's best to show and demonstrate all the history of the training. So we would like to plot the accuracy and the validation accuracy in a one diagram, and also to the same for the lost and the validation lost. So since all the history was stored in the result variable, we plot the training and the validation accuracy and visualize it to understand the model performance. So these are the commands in order to extract and show it on a graph, one for the validation and one for the loss. Okay, we have to fix it. It should be as a string. Okay, let's fix it as well. Okay, we are ready to run. And let's watch the training. As you can see, it will be 300 epochs, but we are not going to wait 300 epochs. We'll jump directly to the ending process, but it's very important that you can see that each time the validation is being improved and new weights are being stored to our best model file. So let's run it as fast forward and jump directly to the final step of the training. Okay, you will see now that the training was stopped after 33 epochs. The early stopping process has finished the training. You can see that the training and validation accuracy is very good, and also the loss. And we have a best validation accuracy of 0.92, a very good one. So now let's test our model with a new and fresh image. Let's see, this would be our image. It's a water polo image. We would like to test it on our new model. So let's create a new Python file and let's start the coding for testing our new image. So we will start with importing the required Python libraries. Of course, we will import TensorFlow and OpenCV in order to show and do some manipulation on the images, and along with other necessary modules. Let's define our image size, which is the same, 224. We have to convert our fresh new image to the same image size. And now let's get the name of the classes. In order to do that, we will specify the path to our main dataset folder and retrieve all the class names, which is the name of the subfolders. And this will help us to interpret the model prediction. The model prediction will generate or return a value, and we have to convert it to the name of the class. Next, we will load our best model, the one that we saved earlier. This brain model stored in a specific file, so we'll use the load model in order to load the weights. Now we are defining a function that will help us to convert and to load and convert our fresh image. And this function basically it's a pre-process for images before the prediction. So it loads the image, resize the image to our desired dimension, then it converts all the image to a numpy array, and then normalize it to our pixel value. It also adds a new dimension, since we are expecting, our model expects for a batch of images, so we are adding, using the expect dims, another dimension for our image. Now let's pre-process our test image using this function, this prepare image function, so it will be compatible for our model. So we're using the OpenCV in order to load and read the image, and we are using the same OpenCV functions in order to display it. So yet we didn't do any prediction, we just would like to show our image using OpenCV. Okay, this is a result. As you can see, it's a very big image. We would like to resize the display of the image. This resize process is only for display, it's not for the model. As for the model, as I mentioned earlier, the prepare image doing the resize for 224. As for display, let's resize it by 60%. So we are resizing the width and the height with the same scale percentage, and we will use the OpenCV function in order to resize the displayed image, and then we will run it again, and we are expecting to see a smaller image that will fit our screen. Let's run it. Great, as you can see, it's a smaller image, it's fit our screen. So now we can continue to the next step, which is running the prediction. So let's prepare our image using the function, and then we will run the model prediction using the predict function, and the result will be stored in the result array. Since our model gets prediction for 10 classes, let's get the higher value and let's print it. We will use the argmax in order to get the higher prediction, which indicates which of the classes is the best one, the best predicted one. Okay, as you can see, the value is 8. So what is class number 8? As for that, we have the class's name that we loaded earlier. So let's get the description of the value 8 using the classes list. And let's print it. And this will be the predicted class of our model. Let's run it again. As you can see, the value is water polo. Great, that means that our model works perfectly. So let's go for the last step. We would like to show it along with our image, so we will use the putText functions. We would like to put this description, this water polo description, inside our resized image. So the 10 by 100 will be the position, and we are choosing the font and the size and the color of the text. It's a straightforward process using the put text function using OpenCV. Let's run it again. So basically we're expecting to see the image with the text, a blue text inside it. Great, this is the result. Thank you very much. You are most welcome to subscribe my channels. Link for the code will be in the video description. Bye bye.